We'll be looking at past questions and 50 likely Jamb questions on organic chemistry. So let's look at first question. Organic molecules that have the suffix ENE are unsaturated hydrocarbons that have, okay, so ENE are for alkenes. Okay, so the answer, and alkenes tend to have double bonds. Okay, so the answer will be B, the double bond. Okay, the other unsaturated hydrocarbon are alkynes. Okay, and alkynes have a triple bond. The functional groups present in the compound above are, so for the functional group, so we have, let's circle this functional group, we have, this is a functional group, this is another functional group, this is another functional group. Okay, so these two functional groups are called the halo groups. That's because they are from the family of halogens. Why this is called the hydroxyl. Okay. So the answer to this question is hydroxyl and halo group. That's option. That's D, hydroxy and halo group. Okay, don't confuse it for chloro. Although this is called chloro, but they all belong to the halogen. Let's look at the next question. Alright, the IUPAC nomenclature of the compound above is, okay, before we name this compound, the first thing we have to do is I'm going to redraw the compound. So this is, so to redraw the compound we have CH3. Then we have, for this, okay, I'm going to spread it out. It's going to be CH2. Okay, you can see we have in bracket 3, so that means this CH2, we have 3 of it, so that's for that. So the next one is this, so we have CH, okay, then we have C2H5. Then for this, okay, I'm going to do like this. This is C3H7. Okay, when naming, before you name the organic compound, the first thing you have to do is you have to find the longest chain. You have to find the longest chain. So the longest chain is going to be your root chain. So now, how do we get the longest chain? So let's count. This is 1, this is 2, this is 3, this is 4, this is 5. This is 6. We have 2 carbons here, so it will be 6 and 7. So from here to here, we have just 7 carbons. But if you count from here down to this place, okay, so let's count. We have 1, we have 2, we have 3, we have 4, we have 5, and then plus this 3, we have 8. So let me just let me withdraw this. So this will be CH2, CH2, and CH3. So we have 5, 6, 7, and 8. So since we have 8 carbons, okay, here, so that means this will be our longest chain, okay, from here to here. So that means this group here becomes a substituent. So now let's name, okay, so to name this compound, okay, our numbering, our correct numbering is going to be okay, from here, I'm going to number from here, 1, 2, 3, 4, 5, 6, 7, and 8. Okay, the reason why we are numbering from here, okay, from this place to this from the right to the left is because we want the substituent here to have a low number as possible. So because if we number from left to right, okay, this substituent is going to be on the 5th carbon, which is this. But if we number from right to left, the substituent is going to be on the 4th carbon. So you want the substituent to have the lowest number as possible. So the first thing you have to do, so let's write out the substituents. So we have 4, we have ethyl, the substituent is ethyl, and then you now name the root, the main chain, okay, which has 8 carbons, so which becomes 4-ethyl octane. So the answer to that question would be A, 4-ethyl. So to name this hydrocarbon, okay, so let's redraw the structure. We have CH3, okay, so we have CH, and then we have CH3, the substituent there. So we have CH, then we have CH2, and CH3. So we have CH2, then we have CH, then this, okay, this substituent, this looking like a substituent here, I'm going to make it part of the chain, the main chain. Why? Because we cannot have 2 substituents on the last carbon. We cannot have 2 substituents on the last carbon. It is wrong. So this will remain as our substituent, CH3. So from here now, so the first thing you have to do when naming hydrocarbon is to, okay, let's number. That's the first thing. Let's number. We'll number from left to right. 1, 2, 3, 4, 5, and 6. So we have in the main chain we have 6 carbons. So now let's look at the substituent. So for the substituents, we have this methyl, we have ethyl on the 3rd carbon, we have another methyl on the 2nd carbon. So we have 3 substituents, but the substituent needs to be written alphabetically. So this is methyl, and then we have ethyl. So E comes before M. So we have 3 ethyl, then we have 2,5-methyl, okay, and so that's all for the substituent. So we name the main chain, which is called hexane, since it has 6 carbon. So we have 3-ethyl, 2,5-dimethyl, sorry, there's supposed to be a di here because we have 2 methyl groups, so we put di. So our answer is option A. So that is our answer. So that's for that. So let's go to the next question. From here, let's redraw the structure again for clarity purpose. So we have CH2, okay, we have double bond, we have C. Like I told you, this is looking like a substituent, this is looking like a substituent. We can't have 2 substituents on the last carbon. So take note of that. Can't have 2 substituents for the last carbon. So we have CH3, and then this is going to be part of the main chain. So alright, so let's circle out our substituents. We have this is a substituent, okay, and then so let's number now. So we have we'll number from the left to right, okay, 1, 2, 3. We are numbering from the left to right because we want to give priority to the functional group, which is the double bond. So we have 2-methyl, 1 substituent. We have another substituent here, which is on the 3rd carbon. So we have 3-chloro. So we have 3-chloro, 2-methyl, then we have prop 1-ene. 1-ene because the double bond is on the 1st carbon, okay? Yeah, it's between the 1st and the 2nd carbon, but we'll give the double bonds to the carbon that has the lowest number. Take note of that. So this is 3-chloro, okay, 2-methyl propene. So you can see chloro came before methyl because you have to name your substituents alphabetically. So take note of that. So let's go to the next question. Now, which of the following is used to hasten the ripening of fruits? So we have the answer to this question is ethene. Ethene is used to hasten it actually hastens the ripening of fruits. In fact, most plants tend to have this as part of their hormones, okay, which boosts the ripening of fruit. So let's go to the next question. All right, the final products of the reaction between methane and chlorine in the presence of ultraviolet light are hydrogen chloride. And so this reaction is a very common reaction among alkane, so which is called substitution reaction. When you have, for example, methane, okay, CH4 reacting with chlorine gas, the hydrogen will be substituted, will keep on being substituted till all the hydrogen has all been replaced by chlorine. So for example, this methane reacts with chlorine, we are going to get CH and 3, so one hydrogen goes, and then plus HCl. So HCl is always the byproduct. So the products, the chloromethane would continue the second phase of the reaction, okay, reaction under chlorine gas, and then it will give us dichloromethane, which is CH2 and Cl2. So 2 hydrogen has been replaced by 2 chlorine. So the dichloromethane would continue the reaction okay, to give us trichloromethane. So 3 chlorine. So trichloromethane would continue the reaction to give us tetrachloromethane, which is CCl4. Okay, so when all the hydrogen has been substituted for chlorine, so the reaction stops. So the answer to this question is C. Okay, so remember the reaction is called substitution reaction. So let's go to the next question. Now, the correct order of increasing boiling points of the following compounds are. Now, in this compound, I want you to understand that compounds that tend to have hydrogen bond, like OH, tends to have higher boiling points than compounds that do not. So therefore, the compound with the highest boiling points is C3H7OH. Okay, so now it's we are left with this and this. So between butane and heptane, okay, when you go to the family of these compounds, the boiling points tend to increase as you come down. So that means heptane has a higher boiling point than butane. Okay, so therefore we have something like this. So since they say in order of increasing, so the one that would have the highest is propanol, second to heptane, then we have butane. So the answer to that question is B. Now, one of the major uses of alkane is, so alkane has lots of uses, but one of the major use is as domestic and industrial fuel. So that's why your hydrocarbon, your fuel, okay, using cars, the fuel using your gas for cooking are actually alkane. So one compound that is used as anesthetic. Okay, so remember, all these compounds are actually products from the substitution reaction of methane. Okay, so the compound used as anesthetic is actually chloroform, which is B. Okay, chloroform is used as anesthetic. It actually makes one to become unconscious, or this is temporarily slip off when the gas is released. So the question says, which of the following can have an isomer? So isomerism starts in alkanes, in alkane compound. Isomerism starts from butane. Okay, now why do isomerism start from butane? Now, for example, if I have butane, which is C, it has 4 carbon, okay, 4 carbon. Now, I can easily write the isomer of butane. Okay, what I simply do is I will take this last chain, okay, and I'll make it a branch chain, and I have something like this. So it becomes a branch chain. Okay, so now this is an isomer of this compound. Okay, now for example, if I have this, I can't use this to make a branch chain, because when you are trying to make an isomer of a compound, okay, by using one of the carbon to make a branch chain, the branch chain, this branch chain or the substituent cannot be on the first or on the last carbon. It must be on the carbon between the first and the last. So if I take this and if I try to make this compound to be an isomer, it's going to be look like something like this. So this is basically wrong. Okay, this is not an isomer, because this and this are basically the same thing. So the compound that would exhibit isomerism is B. Now, which of the following types of reaction takes place between ethane and the halogen? So remember, I said one common reaction among the alkane, because this ethane is a member of the alkane family. So one common reaction is the substitution reaction. So the answer is A. Alkanoids are formed by the reaction of alkanoic acid with, so alkanoids are actually esters, okay? They are called esters. So this question basically is asking you how are esters formed. So esters are formed by the reaction of between alkanoic acid with alkanol. So now the functional group present in the compound above is, so this compound, okay, if you look at it, it might be deceiving, okay? So if you look at this, you are seeing two functional groups. One of them is the double bond, and one of them is the carbonyl group. So now, there is something we call order of priority, okay? For order of priority, when you see a compound that tends to have two functional groups, okay, for example, like this, the carbonyl group has a higher, or it's prioritized over the double bond, the single bond, or the triple bond. So therefore, the answer to this question is alkanal. Okay, alkanal. Okay, so that's the answer, because it's prioritized over the double bond. Let's go to the next question. Now, what is the IUPAC name for the following compound? So this compound, the IUPAC name, it has a triple bond. So the IUPAC name is methyl acetylene. The organic functional group which can likely decolorize ammonical silver nitrate. Okay, the set of organic compound that decolorizes or forms white precipitate of ammonical silver nitrate is called alkyne. Okay, so the answer is C. And the group of alkynes that actually not all alkyne does this. The group of alkyne that does this are the terminal alkynes. So what are terminal alkynes? Look at this, for example. So this is an alkyne. This is an alkyne. It has triple bond. I'm going to draw two alkynes. Okay, so now terminal alkynes are the alkynes that have their triple bond at the first carbon. So this is a terminal alkyne, why this is not. When excess ethanol is heated to 145 degrees Celsius in the presence of concentrated sulfuric acid, the product is diethyl ether. Two organic compounds K and L were treated with a few drops of Fehling solution respectively. K formed a briquette precipitate while L remained unaffected. The compound K is, and so the answer to this question is alkanal. Now this test using Fehling solution is used to separate alkanal from alkanone. Okay, so alkanal give a positive test while alkanone does not. So that's why C is the correct answer to the question. So let's look at another question. Which of the following statements is true about 2-methylpropanol and butane? Now let's look at the structure of these two compounds. So we have 2-methylpropanol, so we have CH3, so this is 2-methylpropane rather, and then we have butane. This is butane, CH3, CH2, and then CH3. Now if you look at both of these compounds, you can see that their molecular formula are both the same. This is C4H10, okay, and then this is C4H10. So let's look at the answers, the options rather. They are not members of the same homologous series. This is wrong. They are both alkanes, so they belong to the same homologous series. They have the same boiling point. No. Branch chain have a lower boiling point than unbranched chain. So this is wrong. B is wrong. So C, they have different number of carbon atoms. No, the carbon atoms are the same. This is wrong. They have same chemical properties. Now this is correct. Correct because compounds that belong to the same homologous series tend to have the same chemical properties. So let's look at another question. Now, with concentrated H2SO4 as catalyst, ethanoic acid reacts with ethanol to give us ethyl ethanoate plus water. So this reaction is called esterification. Remember, esterification reaction is a reaction between alkanoic acid and alkanol. Okay, so when alkanol reacts with alkanoic acid, it will give us an alkyl alkanoate, which is called an ester. So that's for that. Let's go to the next question. Now, which of the following is acceptable as the organic product of the reaction between ethanoic acid and ethanol? So just like the previous question we just saw, the answer is ethyl ethanoate. So that's A, ethyl ethanoate. Okay, so that's also a esterification reaction. So let's look at the next question. So methane is a member of the homologous series called, the answer to this question is alkane. So methane belongs to the homologous series called alkanes, and the general formula is CnH2n plus 2. Okay, so if you want to write the formula of methane, so methane has 1 carbon, so it becomes C1 H2, your N is 1 plus 2, so this becomes CH, 2 times 1 is 2 plus 2, that's equal to 4. So this is methane. So let's go to the next question. The compound above exhibits, okay, so for this question the answer is B, okay, optical isomerism. Now before I look at why, let's explain the different types of isomerism you have in the options. So we have geometric isomerism. Now take note, geometric isomerism usually occurs in compounds that have double bond. For example, you have this, you have Cl, and then we have Cl, okay? You have H, and then you have H. So then you have C, and then you have C, and then you have Cl, and then you have Cl, then you have H. So this is geometric isomerism, occurs in compounds that have double bond. Now, why for optical isomerism? For a compound to be able to exhibit optical isomerism, there's something we call asymmetric carbon. Now, what is asymmetric carbon? Asymmetric carbon is a carbon which is at the center of a carbon of an organic compound that has different functional group attached to it. Okay, now let's look at the diagram I'm trying to draw. If you look at this is an asymmetric carbon. It has different functional group attached to it. Okay, so the isomer, this compound will exhibit optical isomerism. So let's look at the question. If you look at this, it has different groups attached to it. There are different groups attached to it. Okay, we have hydrogen, we have the carboxyl functional group, we have hydroxyl, we have the alkyl functional group. So these four attached to the center carbon, which is the asymmetric carbon, are different. So we call this carbon asymmetric carbon. Now, why for structural isomerism, it occurs majorly in compounds that are alkanes. Okay, alkanes, for example, let's take a look at this. You have C. Okay, you have this. Okay, you have this. You have this is butane. Okay, so if I want to make a structural isomer of this compound, what I will just simply do is I will take one of these carbon and make it a branch chain. So I'm going to have something like this. So these are structural isomerism. While lastly, the last one, which is positional isomers. Positional isomers are, it occurs, it is quite versatile. For example, let's say you have this. Okay, this is the first carbon, second carbon, and third carbon. So let's say I have a chloro group attached to the second carbon. To make an isomer of this, what I'll just do is I will change the position of the chloro group. I can take it to the first carbon. Okay, I can take it to the third carbon. Okay, so that's positional isomerism. So that's the difference between the four isomers and the options. Let's look at this. So the answer here is